Hi, my name is Jay Barkala, and this is my presentation on Lab 3 beam vibration. The objective of this lab is to record the free vibration response of a cantilevered beam using strain gauge with a Wheatstone bridge to analyze the free vibration data to find the vibration parameters of the system, to compare the experimental system response to the theoretical response given the same parameters, and to find natural frequencies and modes using spectrum analysis. The equipment used in this experiment are a metal ruler with a strain gauge attached and a Wheatstone bridge, an MSP432 with a PEP kit, a laptop running the MSP432 GUI on MATLAB, and a clamp setup with aluminum and wooden blocks. The metal ruler was clamped to the table between the wooden and metal blocks and held with the 3-inch mark at the edge of the table. The strain gauge was also hooked up to a Wheatstone bridge that's connected to the MSP432, which is set up in the GUI doing high-speed data acquisition with a sampling frequency of 2000 hertz and a buffer length of 15,000 samples. There were 4 experimental cases performed and recorded. Case 1 was initial displacement excitation, which involved displacing the tip of the beam by about 20 millimeters. The case 2 was impulse excitation, which had a coin dropped on the beam tip. And cases 3 and 4 were identical to case 1 with 2 varieties of tape to provide damping. In lab 2, static measurements were taken by incrementally adding weights to the tip of the beam and recording the strain gauge output voltage. This was used to create a plot which was then fit with a linear fit model. And this allowed us to find a sensitivity of 15,072 millimeters per volt. This same process was done to find an equivalent spring stiffness by plotting the data and finding a linear fit. And this is going to be used later to find the theoretical response of the system. Um, in our experimental data, uh, as you can see the free vibration response in the plot on the bottom right. Uh, as you can see, the displacement magnitude is greatest at the point of release around 1 seconds, and the rate of dissipation appears to be linear with the beam still oscillating at the end of the data collection period. A few system parameters were estimated using this data. The damp natural frequency was found by locating the peaks in the plot that was shown before, and choosing an arbitrary interval of peaks in the center of the data, finding the average time difference between these points, and then taking the inverse of that value. Damping ratio is found by performing a curve fit on that interval of data, and then taking the rate coefficient from that curve fit uh, as it represents the term negative zeta omega n, and then plugging it into this equation. The result is then multiplied by 100 to find the answer in percent. Natural frequency is found by dividing the term zeta omega n by the determined damping ratio. The damping ratio of 0.223% indicates the system is underdamped. This is the equation shown to theoretically model this response. This is the standard uh, equation for the response of a single degree of freedom mass spring damper system, uh, which has x double prime as acceleration, x prime as velocity, x as position, f is forcing, which was 0, c is the damping coefficient, which was found earlier, k is the equivalent spring stiffness, which was also found earlier, and m is the equivalent mass of the system, which is a ratio of the actual mass of the beam. And as you can see, the theoretical response matches quite closely to the positive deflection, particularly of the experimental response, although there is a notable gap in the negative side of the deflection. Spectrum analysis on the data was computed by performing a fast Fourier transform, and it shows a prominent peak at the 12.4 hertz frequency, indicating that this is the first mode natural frequency. And it is slightly lower than the value calculated from the time history earlier, which was found to be about 14.27 hertz. Impulse excitation was done again by dropping a coin by approximate height of about 4 to 6 inches. Uh, the displacement over time for this response was much more evenly distributed for positive and negative displacement, and the dissipation of energy was also more rapid. Spectrum analysis on this data indicates that there are two modes. The first mode, natural frequency, being at 13.6 hertz, and the second mode, natural frequency, being at 84.9 hertz. And the first natural frequency is also slightly lower than the value calculated from time history, which was found to be about 14.3 hertz. Uh, this is case 3 and 4, which again was identical to case 1, but about 5 inches of damping tape were applied to the underside of the rulers. Um, for case 3, 2 layers of painter tape was used, and case 4 used a layer of double-sided tape, which was much thicker. Um, and these were the results. As shown, tape 1, which was painter's tape, had a slightly higher damping ratio, while tape 2 had an even higher damping ratio, as expected, because the double-sided tape was much more resistant to bending and thicker. Uh, case case 4 had an almost return to equilibrium within 3 to 4 seconds, while case 3 took longer than 7, and the undamped case took even longer. A summary of the data is presented in this table here. These are the estimated beam parameters. As you can see, all the first natural frequencies are approximately equal, um, more or less, with an increasing damping ratio from case 1, 3, and 4, and case 2 having a slightly higher than expected damping ratio than case 1, despite both of them having no damping. Um, And in conclusion, natural frequencies are relatively unaffected by damping. Tape can serve as a weak damper for the oscillation of a cantilevered metal ruler, though all cases were underdamped. Uh, Theoretical models of oscillation using an equivalent single degree of freedom system can be effective in predicting the behavior of a physical oscillating system. And fast Fourier transforms are an effective way to find the natural frequencies and modes of a noisy oscillating signal. And these are my references. Thank you.